So P7.2, discovery of the nucleus. Now this is an absolutely crucial experiment that you need to know about. It comes up on both your chemistry and your physics. In chemistry they call it the gold leaf experiment. In physics we call it the Rutherford scattering experiment. Okay, so here's the thing. To start with, there was a model of the atom, and it explained everything that they needed to know at the time. And that model of the atom was this. It was that you had a positive charge, and inside that positive charge you had some electrons. And those electrons provided your negative charge, and the protons provided your positive charge. And crucially, it was all just spread out and there's no space anywhere. And that was called the Plum pudding model. And the reason why you needed this model was because they discovered that there's such a thing as negative charge and there's something called positive charge. Okay, so we needed to say, how's that spread out within the nucleus? So people just guess, well, you know, particles are pretty solid, so therefore there can't be any space between them. Okay, and then what Rutherford did was he looked at a type of radiation called alpha radiation that we mentioned last lesson. Now, alpha radiation has got two positive charges and two neutral charges. Now, Rutherford didn't know about those neutral charges, but he did know about the positive charges. So he knew that the alpha particle was positive. Okay, so he was aware that the alpha particle was positive. And he then used that fact to explain the next bit of information. Okay, so he fired those alpha particles at a gold sheet, and the reason why it was gold was so that he could hammer it so it was so thin that it was nearly only one atom thick. And the reason why he wanted it to be one atom thick was so that when the alpha particles went through the gold, they would only be interfering with one of the gold particles. Okay, because if it was lots of them, you wouldn't know what each individual one was doing. And most of the particles went straight through. Most of the alpha particles went straight through. And that was what he was expecting. But what they did was they had a scanner like this, and they had a source inside a shielded box so that the alpha particles could only get out in one direction, and the gold was here. So that's your gold. This is your source, it's right in the middle there. And that's an alpha source. And this is the shielding. And it's a lead box. The shielding will be a lead box to stop them from getting out any other way. And then this entire circle here, that's a screen. And what he did was he had a detector that went around this screen, and if an alpha particle hit the screen where the detector was, there'd be a flash of light, and he could detect where that flash of light was. So using this method, he moved this detector all the way around the source, even behind it. And what he did was he measured the angle that had been deflected, so how much of that alpha particle had been deflected by. And what he noticed was, he noticed that instead of the atoms going straight through like he had expected, some of them were deflected by an angle. And what's happening here is, we know that this is a positive charge going in, so we talked about that, okay, and it's being deflected, and some of them, not many, were repelled by it full on. Now, you already know from electricity, something that will repel something else. You know that like charges will repel. You already know that from electricity. So in that case then, what is it that's making these alpha particles either change direction or sometimes even bounce straight back? And what Rutherford suggested was, he suggested that in the middle of those atoms, there must be a positive charge. And that positive charge in the middle of these gold atoms is what is repelling these. So when the alpha particle gets close enough, sometimes it's bounced straight back, and sometimes if it doesn't get too close but gets deflected off, because it is always going to be deflected away because like charges repel. Okay, so, and this would have been the angle that they then measured. That would be the angle that is deflected by. Okay, now he had a problem here, and that if the Plum pudding model was correct, then his problem's this: that positive charge is too spread out, it's too thin. It wouldn't be concentrated enough in one place to be able to repel or deflect these alpha particles. The alpha particles would just go straight through it, because it'd be like firing a machine gun at a plum pudding, and some of the bullets bouncing back. It just wouldn't happen. It's not dense enough. So what he said was, all of the charge must be concentrated in one small area, in order so that when the alpha particle hits that small area, it is dense enough to bounce it back or to deflect it. And we now call that small area where all the positive charge is concentrated, we now call that the nucleus. So that was the first discovery of the nucleus. Up until then, he thought it was all spread out in a plum pudding model, where all of the positive charge was just spread out everywhere. Okay, so it had to be concentrated in one area so that there's enough in one place to repel the alpha particles. And then that left a problem. Where's the negative charge? If that's where all the positive charge is, then where's the negative charge? And it led to another problem, and that was, well, these nucleuses, they're too heavy. How can they be that heavy? Because based on the charge that we've got and the mass of gold, we're missing something. So what are we missing? And that was what they had to do next when they discovered the neutron.